1.0.
Right. So these were all. Yep. Yep.
It should still be the same.
Yeah, you'll just be off by a decimal point.
Okay.
But yeah.
I just have to redo these.
So,
It should just be the same. Just one.
but you have them flipped.
Oh, I will.
Yeah.
Do we have
Here, I can go look on my email.
two hundo cents.
So apparently I flipped them. So these aren't even right. Oh, but Britta's got them.
Oh, so she did it.
Yeah.
Okay.
Oh yeah, you did put the wrong one on. Yep. And we were supposed to measure not to 10, but to 1. So yeah, everything's like, I don't know. Bridget's got the right one though. Okay. You just have to change it in your book. Sure.
Are you playing in a parade stuff?
Oh, it's.
You're gonna need
That's
to.
okay. How long are you guys
Remember, we want to organize those based on what group you paired up with.
This one was 27.
They picked the last one, right? I think that one chick that's named I would not have. They all wanted it. Usher.
I'll just.
I never watched it. So you print them off. I know. I had What is it called? It's like where within their own team they have
You go. This is. This is.
Yeah, good. Good. So let's know what's that.
I don't know why.
Didn't even like
Everything was like cracking and it was so hot and the lake was cracking and it was falling and like everything was just like
Multiplying by.
Yeah, that would be
This
weird
is
to have
coulombs per second.
yeah, like when the noise
So invert it and simplify it.
so loud and it's like scary sometimes. Personally proud of
And then, but it's interesting because we'll come back and look at something like this.
All right, folks. I believe we're just about ready. The last board is on its way up. You have your lab journal open.
I don't know.
And we did organize them based on our partner, right? Our other group. It looks like we did.
Okay, disregard my drawing. Can I go change that? I'm gonna go change that. Just don't even look at
Okay,
All right, looks good. Let's take a look at all of the boards. It looks like we're in unanimous agreement as to the overall relationship. Right?
Yes.
Linear, positive slope. What about an intercept?
No.
No intercept, okay? So we can write that the electrical potential difference is proportional to the current, and let's add that there's no intercept. Why does it make sense that there would be no intercept for this?
When you have no charge.
Whoa. Go ahead, Carrie. Good. Emily, did you add something to that? Okay, Caitlin. And that makes sense. As a matter of fact, how many groups use that as a valid data point?
I just clicked out a skill from 0.
Could we use it as a valid data point?
Yes.
Sure. While you were patiently waiting for me to come and check your circuit, you saw that when the electric potential difference was set to 0, you had a current of 0. So if the electrical potential difference is the energy per charge and there's no energy per charge, it would make sense that there's going to be no flow of charge. Let's put the graph itself into conceptual terms. Go ahead, Molly.
As the current increases, so does the electrical potential difference.
Good. So as the current increases, so does the electrical potential difference. Let's take a look at the slope. What's one of the first things that you notice?
Positive.
Okay, positive, good. Anything else?
A lot of people have different units on there. Some people have volts per amp, some people have joules per seconds per coulomb squared.
Okay, and we can see in a little bit if those are the same. Emily, what did you say? Yeah, the units are a bit interesting. What about the fact that we have two different values for each group? Yeah, it's not a universal constant. So in this experiment, whatever the slope turns out to mean, it's not one of Mother Nature's magic numbers. It's not a universal constant. So let's put that down. So if it's not a universal constant, but it is linear, we know that it's got to be constant for something. For a particular group, and what was different between the groups? The spool. So it would be constant for a particular spool. That makes sense to everybody? Good. In the pre-lab discussion, we brought up some things about the spool that might affect the relationship. Molly?
The gauge, the length,
Okay, the gauge, the length, and the material. probably should review the idea of the gauge. What did that specifically relate to? The thickness or the cross-sectional area? Okay. What I would like you to do is to look at all of the boards now. You'll have to use your own, of course, too. But look at all of the boards and see if you can determine what the relationship is then between the slope value and the thickness of the wire. Charlie?
The thinner the wire is, the bigger the slope.
The thinner the wire, the bigger the slope. It seems to hold true for this one. They had a 26 gauge and a 30 gauge. Okay. So it holds, definitely holds true for that one. For this group, what was the factors that you looked at? So you did length, okay. Length, length. How about this group? What relationship did you?
Length.
Length?
Yeah.
Gauge, so thinner wire. Can we all agree on that? All right, let's add that. So the slope value is greater with thin wires. How about for the length? Greater the slope, the greater the length?
Yeah.
And that holds true for all of them? Okay, I would agree with that. Let's take a look at the units themselves so that we can see if everybody has the same set of units and then use the units to figure out conceptually what it means. If we go back to the original graph, I think, weren't we plotting the potential difference in joules per coulomb? And then the current was in coulombs per second. Did we simplify? Some groups did? Yeah, it's kind of interesting. Joule per coulomb times seconds over coulombs. So we get joule dot seconds over coulomb squared. This, by the way, would also be a volt over an ampere. Did anybody take it beyond the joule? What's inside of a joule? Newton dot meter. Did anybody take it that far? Or did anybody take it beyond that, even what's inside of a Newton?
Should we do that now?
We could, but what do you think when you're at this point right now?
The amount of energy.
Well, yeah, I mean, if we've got to this part so far, even if we just think about, all right, inside a joule is a Newton dot meter, that would give me a Newton dot meter dot second over coulomb squared. It doesn't look like it's going to get any easier, and it doesn't look like it's going to become something we recognize. So for us, when it's not easier and it's not something we recognize, what does that tell us? Yeah, it's a new quantity. It's some new constant. right? Now let's narrow in on what it is. I'd like to start, I think right here. We know that that's the electrical potential difference, and we know because the units are joules per coulomb, that's the energy each coulomb has or needs for what would be in the denominator? Okay, what particular rate?
Rate of the flow.
Yeah, what in this case, even though we haven't written a number and you haven't written a number, what number's in that denominator? So it's the energy each coulomb has or needs for a current of 1 coulomb per second or 1 amp. We're okay with that? It definitely relates to energy, and it definitely relates to the energy required for a particular rate. Now, when you compare two of the spools,
To the same schools?
well, let's do two different spools. For example, if we take, I'm gonna steal your marker. If I take, let's say, this particular board, and I pick, this particular current, right there. To get that current for the 26 gauge, I only need that particular potential difference. Or even if we wanted to say 1 amp, I need about 15.5 joules per coulomb. But for the same current, I would need a much bigger one. So as the wire gets longer, there's more, as the wire gets, that's not a length one. As the wire gets thinner, to keep the same current, there has to be more energy per charge.
They're already getting the input.
It could be. But it almost seems like there's something about that situation that's opposing the flow of the charges. That makes sense? Because it requires more energy, there's got to be something about it that's opposing that flow of charge. So to conceptualize this a little bit more, we can think of it as the opposition to charge flow. So thinner wires have more opposition to charge flow. Longer wires, more opposition to charge flow. Let me give you maybe an example, a little bit of analogy. Yeah?
Thinner wires have more, but then why does the 26 gauge have less?
Remember, the higher the gauge number, the thinner the wire.
Oh, that's right.
So let's just take the analogy that we're going to go out here during passing time. We've got 8 doors, 4 right here, 4 over here. And in a particular passing time, a certain amount of time, let's just say we have to get half the student body, 1,000 people from one end of the building to the other. And with 8 doors open, pretty wide hallway, there's probably not a lot of opposition for you to go that direction, right? But if on some occasion somebody happened to lock 4 of those doors and 3 of those doors, and you still had to get that same 1,000 students from the south end to the north end through that one door in the same amount of time. You can't be late for class, your teacher would get mad. There would be a lot more jostling around. Does that make sense? Okay.
So then jostling around is the increased energy or the increased?
Well, it just means that you have more opposition. There's more in your way. There's more not allowing you to keep that same
But
flow.
you'll still get there.
We would hope you would still get there in time. It's an analogy, so yeah. And just like we've done every time, we conceptualize the slope. It's rather long. We give it its own special name. So this is no different. This idea that's the slope of the delta V versus I graph that relates to how much energy each coulomb has to have for a particular current, that relates to the opposition to the charge flow, that's given its own special name. I'm pretty sure some of you know what it is. Yeah. That's how we define electrical resistance. How about this, the letter we use to represent it?
Omega.
Well, you're one step ahead of me. The symbol for resistance is capital R. And then these units, I'll just rewrite them down here. The units that we started out with, a volt over an amp, which simplifies, sort of, to a joule dot second over Coulomb squared. Those are known as an ohm. So 1 volt per amp is 1 ohm. So we have resistance, which is represented with an R, and the units are ohms. But the ohm is given its own symbol also. And that's what some of you were mentioning. Looks like that. Does it look Greek to you? Yeah, it looks Greek to me too. Greek letter omega. I think the reason they do that, if I write 1.5D, you have no problem saying, oh yeah, that's the potential difference, 1.5 volts. If I write 2.0, A, he's probably meaning 2.0 amperes. If I were to write is it 60 and I forgot the units? Is it 60 for ohms? It makes it confusing, so then there's no question. So the slope of your graph represents the amount of resistance your particular spool had. We've got a couple of values for the same spool. How do you think we could figure out what's the real value for the resistance? Say it again.
Constant analysis.
Well, there might be an easier way. Well, we'll get to a general model. It is not written on those spools that I've covered up. I don't know if those spools are on the internet.
Probably has something that measures ohms.
So you're saying that you've learned to use a voltmeter that measures potential difference, and an ammeter that measures the current. You're suggesting an ohm meter that measures the resistance. Excellent suggestion. There is one. It's, for us, it's not a separate meter. Ours come as part of a digital multimeter.
Vernier?
Well, no, Vernier doesn't have one. Well, they might. We don't have any. Ours are sitting right over there. And what I'd like you to do is send one partner to grab your spool. I'd like you to send the other partner to grab the multimeter. And I want you to measure the resistance of your spool with the multimeter, and then we'll do, as part of your analysis, we'll do a percent difference calculation. you've never used one, then get your hand up and I will help you out with that.
What are we? 8 or 9?
You did both of them. So you're gonna measure both. Yeah, you'll want to measure both of your spools. I'm gonna show you. Is your spool on its way? Michael got it? Grab it.
We need the 200s.
You're gonna measure both of them, but the other group would probably start with that first one.
Let's see, I think, we have this one.
Okay. So this, I'm just gonna grab one of those as a pointer. That would measure a potential difference. That would measure potential difference, current. These, all of these are the ones that measure the resistance. And the number here tells us the maximum amount I could measure. So this would be up to 200 ohms, up to 2,000, up to 20,000. According to our board, all of them were less than 200. So we're gonna put it on the 200 setting. And then one partner probably should hold it, but just hold it and then just make really good contact with that. And if it flickers around a little bit, that just means we don't have the best contact. Pretty close. Try maybe putting it right in on the opposite. So like just poke them right in because they're kind of pointy. You can just kind of stab them right in. Did you see how to use it?
Yes, but we did not get the right number.
How far off were you?
A lot.
Oh yeah, I noticed that, but I was gonna see if you guys could figure out why. There's definitely a reason. You're off by a factor.
Yeah.
20.6.
I'm
That's
gonna
not
guess
too
that
bad.
I'll wait to take it.
We had like 20
That's the 26.
Well, oh yeah, that's why yeah, so why
Is there a
did you use
difference in
mine?
this, how it's measured?
Yeah.
This one's mine, you knew mine was
That scale went up to 10 volts. This scale only went up to 1.0.
So these are all adjustment points.
Yeah, so these are all off by a factor of 10, which would make your slope off by a factor of 10.
Okay. Thank you.
20 million.
Did we? Definitely, you were able to figure it out?
Oh yeah.
Okay. And you were close?
Yep, we were going.
Do make sure you do both schools.
Yep, yeah, they are.
Okay. Did we talk about how to measure it? You were close?
Yeah,
Yep.
but
Now you can attach your Is there any group I haven't?
we're measuring
Let me sneak in and out. No, I'm gonna have you do it, but okay, you're at the right setting because the numbers along here represent the maximum number I could measure. So up to 200, up to 2,000, up to 20,000. Yep, and you know they're nice and pointy. I think you can dig right in. Sometimes it's easier from the top. Just dig right in. Somebody will still have to. But you should be able to get pretty good contact.
Okay, we had 169.
So these, this just tells you what. So you're right. This tells you the value of this.
That one wasn't.
40,000. And they're pointy. So, and when you hold it a little bit, you can just dig those points. I would dig them right into the top and just kind of poke them right in there. And you'll have to make sure that you get a pretty good connection. Otherwise, did you notice it's kind of flashing between a bunch of numbers?
Ours is like 2 like a decimal point.
Okay. I'm gonna grab something. Here's, did you use one of these meters? Okay. So take a look at your current readings, and then take a look at this meter.
Oh, that's your 5 points.
Yep. So the maximum is 1 amp instead of 10. So that just means each one of your currents. So now taking that into account, it's your value is a certain. Okay, and did you check both schools?
No.
Did we figure it out okay? Yes.
Yep.
And you were close?
Yep, really close.
We were 0.4 off for one and then.
Yeah.
And that's the same difference, so less than percent. You can do a percent difference.
That's for analysis.
That would be part of analysis.
Okay.
I think every group has had a chance to measure the resistance. All right, you can shut your meters off. Put them back, put your spools back. And we've got a couple more concepts to wrap up with this one. Remember I said this is the big one. Lots to talk about. Okay, all I'm going to do is I'm going to re-sketch that graph.
Is this for our general model?
We're gonna build our way towards it. Yeah. I just want to take a quick minute to kind of summarize and pull some things together. We had that, and let's just add that. Which one of those, the red one or the blue one, would be, if there was the same material and the same length, which one would be a thinner wire?
Blue. Thinner wire. Red.
Higher gauge, thinner wire. Okay, so this is thinner. That would make this one
Thicker.
a little bit thicker. Which would be a longer wire?
Red.
Red also.
Short.
So if we write the general model, relating the potential difference, the current, and the resistance, we had potential difference on the y-axis, the slope was our resistance, and the current was on the x-axis. There we go. That's our general model that relates all three of them. That one's known as Ohm's law. And the thing that's nice about Ohm's law is that not only does it apply to an individual element in a circuit, but it also applies to an entire circuit. And we're gonna get some practice with it a little bit later on. So essentially, in this particular circuit, the spool was something that was put in our circuit, number one, so that we could monitor the energy a little bit more easily. But also, if you think about it, it kind of controlled the amount of current we had. Because if we change the thickness or the length of the wire, we change the current with the same potential difference. So any element that you put into a circuit that controls the amount of current, that's given the generic name resistor. So in this particular experiment, your spool served as a resistor. It's something that controlled the amount of current. For example, if we were going to do bulb boy again and all I had were let's say 6-volt batteries, but I knew that our bulbs only worked with 3 volts. If we connect the 3-volt bulb to the 6-volt battery, we burn the bulb out. So I could put a resistor in as part of that circuit to control the amount of current that would make it to the bulb. That means I have to give you a new symbol so that you can draw your schematic diagram. So the symbol for a resistor, which your spool acted like, looks like this. So when you wrap this one up and you have to draw your schematic diagram, we'll draw that.
In place of the spool or as
In
the
place
wire
of the spool.
going to the spool?
We'll still draw the wire with our nice lines, but the spool itself,
It's gonna be
that has its schematic symbol. So far, so good? It's a lot so far. We've got essentially 3 more things that come out of this lab we need to deal with. You ready?
yes.
Okay.
I answered for everything.
Thank you, Molly. We said that there were 3 factors that we needed to deal with. We've dealt with the gauge, we've dealt with the length, we've not dealt with the material yet. And we didn't have the spools that were different materials, so we didn't look at that. So we're going to get at that a little bit differently. Imagine that, we'll just go to the page. Imagine that I gave you, well, let's do it this way. Let's start with the length and the gauge, and we know that that relates to the area. We know that the resistance of our spool was proportional to the length, right? Longer wire, more resistance. How would we write it for the area?
Same. Nope. Nope. I should do that.
Inverse.
Yep.
Okay, I would agree with that. So far, so good? We've done other experiments where we brought these 2 together. How would I write those 2 separate relationships as one?
R is directly proportional to the length. How is the inverse of the area?
Length times the inverse of the area, or just, okay.
Wouldn't that just be width?
And we know, we can confirm that because if I hold one of them constant, that's like taking it out of the picture. There's my original relationship. If I hold the length constant, whoops, there's my relationship. We'll put it back. There we go. If I wanted to turn this into an equation, I would have to create a new graph, right? What graph would we have to make?
And ohm. Nope.
Resistance would be over here in ohms.
And then L over A on the x-axis. And then straight. Positive.
Yeah, and it would be linear. And the slope here would represent our proportionality constant to change that proportional sign into an equal sign. So imagine if you all had spools of wire. Oh, go ahead.
What are the units on the x-axis?
Meters over meters squared.
Why Why does that not?
I'm going to show you in just a minute. We could. So you all had spools of wire, and the length and the cross-sectional area, would that be dictated by the type of wire, the material?
Say again.
So if you had a spool of wire, does the length or the cross-sectional area, does that depend upon the type of wire, the material? No. So if I had you do an experiment where you used an ohm meter to gather that, we calculated that, we plotted it, and then we compared it to different materials, do you think you'd get the same slope value?
Yeah.
No. This turns out to be where the material constant enters into it. The material constant is given the name resistivity. Yeah, so you've got resistance and you've got resistivity. And it's represented with another Greek letter, rho.
So it's
Those spools are, you could do this experiment with them. It's a little bit more drawn out than I wanted to take the time to do because we have another one we're going to get to. I'll tell you about that in just a minute. So really, if we're dealing with a wire, which we did in this lab, you could have this model that gets developed. The only reason I bring that up is because when we did that pre-lab discussion, you talked about those three factors that entered into what might affect the relationship.
Going back to the graph for a second. So you're saying that if we had two different spools that were both the same width and gauge, but made up of different materials, they would have different slopes.
Exactly. If they were the same length, the same gauge, but one was copper and one was nickel chromium, they would have different slopes there. And that's the experiment that gets at that material constant. Resistivity is a lookup value. What about the units? What units would it have?
Ohms per meter. Nope. that's
Ohms
not-
per meter?
Yeah.
Would be ohms times meters. Because we know that this would have to come out in ohms. This is meters, and that's meters squared. And that's why I didn't simplify it right away. So this has to come out in ohm dot meters so that we get it. Wow. I told you this was a big lab, right? You've got this idea of resistance. You've got the idea of unit ohm. You've got this resistivity that's the material constant. We're not quite done. What we haven't talked about is another place that we sometimes get data from a graph. We get it from the slope. We get it from the intercept. We get it sometimes by the area that's trapped by a graph. Well, in this experiment, in this lab, we have joules per coulomb, coulombs per second. We're about to get to Bell, but I want you to think about if that area trapped represents anything that's familiar to us. You've got it already? I think I heard some units being thrown around.
Shout it out. Joule.
Simplifies to joules per second.
Volt.
Joule per second. Energy, it's the rate of energy transfer. The rate, not just the work, but it's the rate at which energy gets transferred.
Power.
That's electrical power thing now.
That was all even. I just said this thinking I could.
What we'll do tomorrow is we'll talk a little bit more about that. The other piece that we didn't quite get to today is, what if I gave you a second spool, they had 2 at once, and I said wire that into your circuit and see if it affects it.
It depends on if it'd be a series or parallel, wouldn't it?
So you're thinking that there's one relationship between the resistances in series and resistances that are wired in parallel.
We would have to connect that. wouldn't we?
Yeah, that might be an interesting thing to investigate. That does sound like a new lab.
Is that in lab for tomorrow?
That could be a lab for tomorrow. Or at least we got started.
Do we have to do like a one-on-one conclusion?
You do have a conclusion to do for this one. You could get started on it. It's a longer one. Let's make sure your boards get erased and have a safe afternoon.